part of the reason you want to do this is what kind of solutions, okay, let's just address this immediately right now. Suppose I'm solving something like what we've been doing in class. I'm going to solve an equation like this. Heat equation. How many derivatives do you see there? Oh, actually, it's two derivatives. I better make it two-dimensional. Psi xx plus psi yy, right? So we've been solving this in class. And suppose I want to solve a heat equation on some complicated domain and boundaries. All right? How many derivatives do you see? 2. So if I take 2 derivatives of this, what does this always equal? 0. That's a problem. Somehow this is unable to represent any information about 2 second derivatives. However, this I could do. If I take 2 derivatives in x, I get that 2d out, right? So d somehow represents for me information about the second derivative. Okay? So if you have, ultimately what we are going to do is apply it to problems like this. We have to think about, geez, if I'm using such a simple thing, what is it going to do when I start applying derivatives? So there's 2 options. You either go to things like this, but you go, no, that seems so complicated. Because you've got 6 things to worry about, whereas this. So I'm going to, in fact, I like this so much. I'm going to change my problem. I'm going to write it in what's called the weak formulation. So that's 3 and 4. I'm foreshadowing tomorrow. Okay? Not tomorrow. Sorry. Don't come tomorrow. You'll only be disappointed. Come Friday. All right. See, I like to throw teasers out there to get everybody like, oh, I got to come Friday now. Can't wait. It's going to be awesome. Okay. This is what we're working with. This is what we've got to build our solutions in. And remember, it's not just we're solving it some kind of differential equation, partial differential equation with it. Okay? All right. So let's start figuring out how to most conveniently build this thing. So let's start off with 1D simplex. And redraw this figure. And here's my exact solution. Here's going to be my approximation to it. This point here, call it the ith point, the jth point. Remember, I have a bunch of these. I'm going to start with 1D and build up from there. So when I do this, I say, okay, so I've got these points, and this is at x of I. This is at x of j. And what I'm trying to do is fit this line through it. Oop. Okay, so first of all, how do I determine A and B? Now, this is fairly simple. It's 2 equations, 2 unknowns. Okay? But I'm going to set it up in what you might think is an awkward way. But it has a reason. Okay? And ultimately, it's going to give us what the Lagrange polynomials back. And I mentioned those in class, but let me show them to you again here. Okay? So let's go solve for A and B in an awkward way. What will appear awkward at first, but you'll see that it's kind of actually very nice the way we set it up. Okay. Psi of x is a plus bx. I could rewrite that as basically an inner product between 2 vectors. Fancy. See that? I did something, made it harder. But for a reason, as you'll see. Now, let's apply some constraints on this thing. I have 2 constraints to apply. One is it has to go through psi of I. One has to go through psi of j. So what I have then is the following. Psi of I is equal to A plus bxi. Psi of j is equal to A plus bxj. Or, written as a vector system, this, where psi is equal to psi I, psi j, and the matrix A is equal to 1 xi, 1 xj, and then A is written as our unknowns, A and B, I have that system. Okay, so I just took this and wrote it as a 2x2 system of equations. Now, how do I solve it? Well, I'm trying to solve for A and B. So I could say, all right, so pretty simple. If I know the inverse of that matrix, I could just do this. Now, this is a 2x2, and finding inverses of 2x2s is pretty easy. And that's about all you ever want to find an inverse of by hand is a 2x2. And then let the experts at the backslash or inv a command help you out beyond that. Okay, but there you go. You get your inverse, and it's pretty simple to get this inverse. Okay? All right, so to get the inverse, here is the inverse. Let me keep going over here. Oh, I get too low. You have the matrix A. It's given over there. Its inverse, right, is equal to 1 over xj minus xi, xj, xi, negative 1, 1. I'm going to call this distance between xi and xj and xi L. Okay? Oop. Sorry, I think. Okay. All right. So now I'm going to apply that and put that into this formula here. So A is equal to this 1 over L xj, sorry, so, and then this is the inverse, minus xi, negative 1, 1, and then what's over here is phi I, phi j. Again, you kind of go like, okay, why am I doing all this algebra? Seems kind of awkward. I could have gotten this solution a lot easier. But what you actually get out of this, if you multiply this all out, is the following representation. That gives you A and B. From here, you can solve for A, solve for B, and then you can say, well, once I have A and B, remember that psi of x is A plus bx. So if I put in what A and B are, I get the following. Ni x phi I plus nj x phi j. Get this sort of abstract representation where the ni and nj are what's called Lagrange polynomial coefficients. And let me show you what they look like. The ni is equal to 1 over L, xj minus x. The nj is 1 over L, x minus xi. Okay? Lagrange polynomial coefficient. Why is this useful? Notice the way you've set this up. I wanted this thing here to be a polynomial. By the way, this works for any xi, xj, any pair. And what this does is, if you look at this function, what is its value at x of I? Well, put in x of I. Well, let's go start here. Nj, let's put in x of I right there. Nj, put in x of I. X of I minus x of I? 0. Nice. Gone. What about it there? Xj minus x of I? That's L, isn't it? So L over L is 1. So these are like indicator functions. If I'm at xi, this is 1, everything else is 0. And I get back to psi of I. If I'm at x of j, put an x of j here. Xj minus xj, 0. Here, xj minus xi, L over L, 1. This is 1, 0, or 0, 1 at the points. So the Lagrange coefficients give you a very nice representation of how to use these functions. And by the way, once you have this, so we've essentially what we've done for a 2 by 2 system is derived the Lagrange polynomial coefficient formula. So this is a very easy way. I don't have to, once I have this, I no longer have to solve for A and B in any specific case. Okay? I just have a general formula that just gives me the whole thing. Okay? Otherwise, I'd have to solve a 2 by 2 every time I do this. Here, I just write this down directly. Okay? So this is going to be my representation of the solution in 1D between points. It's a line. And if I know what the points are, I can give you all the other values in between. Okay? So that's 1D. That's a 1D simplex.